All right, so now let's do an example of dependent events. Okay, bearing in mind that on the test, it's probably not going to tell you these are dependent events. Okay, dependent again, typically though not exclusively, means that um, you're going to select two or more things, and you're not going to be replacing those things after they're selected. So says we got 24 students in three different majors. None of them have more than one major. Okay, so no item is in more than one group. If an item is in more than one group, then we got to switch things up. Okay, but that we're not going to ever do that. So the professor is planning to select two of the students for demonstration. The first student will be selected at random, and then the second student will be selected at random from the remaining students. The first student is not put back into the pool. Well, that makes sense because you wouldn't want to pick the first student twice, okay, to learn about what's going on. So what is the probability? Oh, probability again. That the first student is accounting and the second student is nursing. Okay, so and means multiply. So the first student is an accounting major. Well, there are 8 ways to get an accounting major out of 24, and you could put 1/3 there. That'd be fine. All right. And then nursing majors. There would be 13 nursing majors out of the remaining 23 students. Okay. And then you would multiply that together. And you would get a 0.1, let's see, was it 3 decimal places? 0.188, which would be 18.8%. I don't think they're looking for the percent. I think we want it like that. Now, what if they said, what's the probability of getting an accounting and another accounting major? Well, it would be 8/24 for the first accounting major. And you're not going to put that accounting major that you just picked back into the pot. So there are only 7 accounting majors left for the second draw out of only 23 students. And that is how you would do accounting and accounting. So I will very likely have one of these on test. I like these. Okay, so probabilities involving 2 rolls of a die. Okay, so and the author goes into a lengthy explanation of what a die is. Okay, so event A, the sum is greater than 8. Event B, the sum is not divisible by 4 or 5. Okay, so what's the probability of event A? All right, now for this, it's really going to be handy to actually write out the sample set. And so for that, I'm going to actually click on their explanation because they show that down below. There we go. So here's the sample set right here. Okay, and they have it like that. They also have it colored. Not totally sure why. Oh, well, that's for part B, I guess. Okay, so the first one was, what's the probability that the sum is greater than 8? Okay, now let me go here. This. Okay, so there's 6 choices here, 6 choices here. So 36 different possibilities of what could happen when you roll 2 dice. You could roll a 1 and a 1, or you could roll a 1 and a 2, or a 1 and a 3. Notice 3 and a 1, that's different. That's considered to be different than 1 and a 3, just as 4 and a 2 is considered different from 2 and 4. That's why you get 36 different choices. Okay, so so we're interested when the sum is greater than 8. Well, no. And you can see they're kind of in order here. I'm just crossing out everything where the sum is not greater than 8. Okay. Now, then I see, oh, wait, that sum is equal to 8. Well, we're looking for greater than 8. So we don't want the sum equal to 8. And so now we can say, oh, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 times out of a total of 36 possibilities that the sum is greater than 8. And that would be your answer. And you just divide that out, 10 divided by 36, and get your answer. All righty. So that's kind of the idea. And I suspect that'll help you with part B. Part B being, okay, what's the probability that the sum is not divisible by 4 or 5? Okay. So you know what? I guess we could take a look at that. I don't know. All those colors confuse me. So let's do this. Okay. So if it's divisible by 4 or 5, the sum, then we're going to cross it out. Well, that sum is is 4, which is certainly divisible by 4. So is that. So those are all the 4s. Here are all of the 8s when they add up to 8. So those are all out. How about things that add up to that are divisible by 5? Well, these add up to 5 right here. So 5 divides into those, and these add up to 10. So 5 divides into them, and I think that's all of them. So we're left with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. All right, 21 out of 36 choices. And you divide that out and you get a decimal. And that's all you do. Not a big deal. Okay, so once again, we've got the standard deck of cards here, represented by everything here, just like that dice chart we saw a second ago. And it says, suppose that a card is drawn at random from a standard deck, so no jokers, it's not like, Old Maid or anything. The card is then shuffled back into the deck. So this is with replacement. So the card is put back. Then for a second time, a card is drawn at random from the deck. So because we put that card back, the probability is not going to change for the second draw. Therefore, these are independent events because whether or not whatever happens on the first draw does not affect what happens on the second because of the replacement of the first card. The card is then shuffled. Okay, finally, for a third time, a card is drawn at random from the deck. Okay, so what's the probability of first drawing a diamond, then a black card, and then a 4? Well, well, well. I'm glad you asked. So the probability of a diamond and a black card and a 4, I think is what it says. Let me double check. Diamond, black card, 4. Yeah. All right. So the and means multiply. And then, of course, the information you don't have in this statement is that you're going to replace the card every time. So there are 13 diamonds out of 52 cards. So you draw out a diamond and then you put it back. So you still have 52 cards to draw from. And there are going to be 26 black cards because, well, half of them are black, half of the 52. And then after you draw that black card, you put it back into the deck. And so you still have 52 to choose from. And how many 4s are there in the deck? Well, there are 4 4s. Okay. And then we multiply it out. 13 and 26 and 4 on the top. 52 to the third power on the bottom. And let's see. That's going to give us, well, let's just say it's not very likely. 0.0, how many decimal places? 4. 0.0096. So that's 0.96%. So just about 1%, about 1% probability. So in other words, if you do this experiment over and over and over and over, you should expect to actually get a diamond, then a black, then a 4, about 1% of the time. Okay. And that would be how to do it. All right, this time we've got, we have dependent events. So I haven't even read the problem yet, but when I see dependent, I suspect okay, we're going to draw a card and then keep it, not put it back into the deck, which of course will affect how many cards are remaining, and therefore, yeah. Okay, so card is drawn at random from a standard deck. That card is not put back in the deck. Okay. Second card is drawn at random from the remaining cards in the deck. Neither of the cards so far drawn so far are put back in the deck. And a third card is drawn. What is the probability that the first card drawn is a 2? Okay. The second card drawn is a 2. And the third card drawn is a face card. Okay. So once again, that and makes multiplication because it's just, the birds and the bees. Whoops, I left off my P. Okay. So probability of drawing a 2, there are 4 2s out of 52 cards, but we don't put that 2 back in the deck. So now there's only 3 2s out of 51 cards. And now there's only 50 cards left. We had 52, we've taken 2 away, we're down to 50. And how many face cards are there? Well, there are 4 kings and 4 queens and 4 jacks. There are 12 face cards. Okay. So let's see. So we're going to get thank you. Okay, it's again, it's not a very high probability, just like we would expect. So we'll get 0.0011, which if you wrote it as a percent would be 0.11%. That's like 1/9 of 1%. So if you did this experiment thousands of times, you should expect to get a 2, then a 2, then a face card. Let's see, this is 11. There's 11 10,000s. So you'd expect it to happen about 11 out of every 10,000 times you do the experiment. So go ahead and do that experiment. I think about 50,000 times ought to be enough. So go ahead. Maybe that's extra credit. I don't know. Okay, so once again, we're doing dependent events, this time involving a survey. All right, no big deal. An internet research company surveyed 90 online shoppers, each of whom made 1 purchase today. So everybody made exactly 1 purchase. The company recorded the type of purchase each shopper made, and here's a summary of what they bought. I'll be honest, I would have definitely not been that, or that, or that. Yeah, I'm definitely that guy there. Okay, 3 shoppers from the survey are selected at random. One at a time, without replacement. So without replacement, it's like that last problem we did where we drew out a card and we did not replace it back into the deck. Hence, dependent events. What's the probability that the first 2 shoppers purchased food? So probability of food and food, purchase food. And the third shopper did pet supplies. Okay. So that'll be this and this and this. All right. And okay, so the probability of buying food, 30 out of 90 people bought food. Okay, that person who bought food, we do not put that person back into the group of 90. So now there's only 29 foodies left out of 89 people. And now there's only 88 people left. And how many pet supply people? There are 32 pet supply people. So as you can see, I mean, there's a lot of similarity here from what we were just doing. I mean, it's basically the same thing. Hope I'm typing this correctly. That would really be cool. All right. Let's see, decimal. Okay, and then it says go 3 decimal places. So we'll go 0.039 or 3.9%. Probability of doing a foodie, then a pet supply person in this situation is 3.9%. Now, if these numbers here change, well, of course, everything else changes. Anyway, that's that.